Hello, guys. Welcome to Programming Club IIT Madras. I am KDVinit. I am currently a newbie at Codeforces. Today, we will be discussing the editorial or the solutions for Codeforces round 763. We will discuss the solutions to the first four problems A, B, C, D. So let's get started. Uh, yeah. Okay. So the first problem is robot cleaner. So I will just explain the question briefly. So what you are given is there is a grid of size n cross m. You are given the location of a robot and a particular place, which is what you want to clean. At each step, the robot would go increment its row index by one and column index by one. So if it starts from here, it will go in this direction. If it starts from here, it goes in this direction. And as it when it touches a wall, it's like kind of gets reflected. So you can imagine it as a light ray has been uh, pointed from this, like from the starting point, uh, in 45 at 45 degree. You know the starting location of the robot, its row and column index, and you know the position of the cell you want to clean. Now, what you are asked is the minimum time at which the cell will get clean. You can read the problem if you want more clarity on the same. So let's just see how the movement of the robot would look like. Like for this particular problem, like for the particular setup that is given here, the robot starts from here, after which it goes here, here. So you can see maybe the movement of the robot can be a bit tricky. Let's see another thing. Suppose it was a bit long, and what could have happened is like it starts from here, it kind of like reflects like this. After this, it goes in this direction. So something like that sort of movement would happen, and you can see the overall movement of the robot would be a bit kind of weird. You can't exactly figure out the pattern. But one nice thing is you can see both the directions are independent of each other. This is like some kind of technique which is pretty common in a lot of problems like these. So you can see the row, like just see the row movement of this robot. Then it first goes here, then it goes up. Like even in this particular problem, like in the setup we had shown earlier, it goes down, then up, then down, then up, then down, then up, so on. And similarly for the columns, it would go in this direction and then in this direction. So we can see that both the directions are a bit independent. And suppose the problem was in one dimension, that like this is what say cell one, and you have n cells. Your robot is on say some particular cell, um, RB, and your cell which you want to clean is RC, or what is it? It's RD. So let's say it's just in one dimension, you have RB and RD. Now what you can see clearly is your robot would go first in the increment direction, then reflect with this, and then come back to here. This is what would happen if the place you want to clean is has a lower index than where you currently are. And if instead it was like the converse, this is the place you want to clean and this is where you are, then you would simply go here. So let's jump into the code now. Um, so I've just solved for them independently and taken the minimum. So suppose for one dimension, your x1 is your current position, x2 is the position you want to go, and n is the length of the cell or the row. Then, if the position you want to go is greater than your current position, then you would simply reach it for the first time, or like the minimum time in x2 minus x1. And if it is less than, then it would be 2n minus x2 minus x1. So it would be n minus x2, n minus x1 to go here, and n minus x2 to go back to that particular cell. For one dimension, you can clearly see that this function would work. And now for this two dimension, since we know that both the dimensions are independent, we can just calculate both of them and take the minimum of them. And that is our answer. I hope the solution is clear. So let's get on to the next problem, which is problem B, game on ranges. Okay, so there is also a nice problem, like a bit maybe harder for a B problem. So for this problem, what we are mentioned, like what we are given is Alice and Bob are playing a game. What the game is, you have a range of numbers, say 1 to n, which is basically like a segment. Yeah. In each step, like uh, Alice will choose a range, which is initially like you just have this particular segment, and Bob will take out one particular element from this. So suppose, okay, yeah. So suppose the uh, segment was 1 to 5, 1 to 8 maybe. Suppose this was your segment, and then Bob decided to pick 4. Then 4 will get removed, and your segments will become like this. If Bob instead decided to move say 1, then this would be your resulting segment. So there's a segment, we select an element, and that elements get deleted, and you get 2 more segments. So at each stage, Alice will select a segment, and Bob will pick an element and delete it. And since you can see that in each step, one element gets deleted. To remove the complete thing, uh, you would need n steps exactly. So let's see, or like say a smaller example, 1, 2, 3, 4. Then a possible way of deleting all the elements could be you first say you first delete 3, which results in this. Then you delete 1, which results in this. Then you delete 2, and then you delete 4, which results in nothing. So this is one way, and you can see there would be exactly n steps, right? So what they have mentioned in the problem, they have given you the n ranges which Alice picked. So each time Alice picked up a range, and you take up a number and delete it. So you are given the range Alice picked up in every move in no particular order. So they could be in like random order, not in the way Alice picked up. And your task is to figure out the elements Bob picked up corresponding to each range. So here, for when Alice chose 1 to 4, Bob chose 3. Yeah. When Alice chose say 1 to 2, here first Alice picked 1 to 2. So let's just write that thing as well. So Alice picked 1 to 4, and our corresponding answer was this. Alice picked 1 to 2, and our answer was, and we chose 1. Then Alice picked 2, we chose 2, no option. And in the end, Alice picked up 4, and we chose 4. So yeah, so this is basically on the right side are the numbers that were picked by Bob, and on the left side is the range which Alice chose. You are given the range Alice had picked over all the queries, and you have to find the corresponding numbers which Bob took. So now it might seem a bit like you might feel a bit difficult. Okay, how can you even figure out what were the numbers? You have like kind of no information on the number. There's nothing to even start from. You are just given the ranges. But one nice observation is, suppose Bob picked up a number, say 3 this in the first range, then you would get 1 to 2, right? To remove all the elements, Alice must pick the range 1 to 2 at least once in the future. So here, as you can see, Alice picked up the range 1 to 2. Say after 1 to 2, we took out 1, and this was the range. Then Alice must pick this range as well at some point of time. So basically, whatever ranges forms in, ls must pick them once at least in the future, so that like the elements in that range can also be deleted. Only like if that range is empty, then yeah, you would not take it. So let me just show you the code that would give more clarity. Yeah, I will just zoom in it a bit. Yeah, so these are the range L and R. You pick up, so like the range which Alice picks up in any random order, not in the particular order. You just go from 1 to n. I'm printing them in the same order as in the input, which is not required. You can print in any order. I print L and R. Now I have to print the corresponding number which Bob picked up. So if Li is equals to Ri, like both the elements are the same, then you know that Bob should have like would have definitely have was forced to pick up that particular number. And in that case, you can print Li and just continue. So that's the answer for this particular range. If these are not the same number, they L and R are different, then what you do is I know that whatever number was picked up, uh, there would be some left element. Okay, so like suppose the range is like 3 to 10, and say Bob picked the number 7, then two ranges would have been formed, 6 and 8, and Alice must pick this range 3 to 6 in future at least once. So what I do is I just iterate over all the particular ranges that are given, and I will find the maximum uh, R corresponding to 3, like maximum right value corresponding to 3, which is less than 7. Because I know this range would have been picked somewhere in the list, and if a range was greater than this, then this would have been 10 or something, which does not indicate uh, like the this particular range selection or the query. And if that R is less than 7, so suppose Alice could have picked 3 to 6, and then maybe in future again 3 to 4, and then 3 to 3. Like suppose these were the ranges Alice picked, then I will take the maximum of them, and I know that its next number was the number that was picked by Bob in this particular query. So for the code, I just go through all the ranges for the range in which L are same. So if Lj is same as Li, then I would check the R values. If the R value is greater than or equal to this particular R, so for this thing, if the R is greater than 10, then it doesn't matter to me. For the first time when R was less than 10, like for all the values which were less than 10, I will just take the maximum of them, and I know that my corresponding number which was picked was mx plus 1. This is something a bit intuitive. You can try out a few examples, and you would be able to see why this works out. So this is more like you can prove it, but I guess it's better if you get the intuition. So yeah, so where you just find out the maximum, and in case there is no other like element that matches, so like for this particular Li value, there was no Ri which was less than 10. That means that the number you picked that time was 7 itself, like 3 itself here. So because like once you pick 3, you would never like find 3 in future. So if the mx value stays -1, you print Li. That way you can answer each corresponding range. You can solve this problem like this implementation is O of n square. You can do it in O of n, I guess, n log n using set and all. But for A and B problems, usually they do allow the timing thing and all. So you can try to exploit it. You can do a better implementation, but it's not required exactly for this problem. Okay. So let's go ahead to the next problem. Um, Next problem is C, balance stone heaps. Okay, so this is a bit interesting problem. Like You can see a few things from the setup itself. So let me just explain you the problem. So you are given a range like n heaps of stones. So let's take say this example. We are given three ranges of stones, like four heaps of stones, 1, 2, and 100. What you do is you start from I equal to 3. You start from I equal to 3. When in this case it would be this element. You go on from here to the right. From this starting from this position, you go on to right. And for each index, what you can do is take some number d, give d to this particular heap, and 2 times d to this particular heap. This way, and obviously this heap should have at least 3D number of stones. For one particular pile or heap, you would do this only once, and you would do this in the this order like 3 to n. You would go from left to right. You can't come back or do this thing again. You will just go through them once and do this operation. Your task is to find the maximum number of stones in the smallest heap. So basically, they have asked what is the maximum number of stones that would be in each of the pile. So you want to maximize the minimum of this particular, like of all the heap sizes. So the solution for this basically, you can see like when there is maximum kind of thing ignored, usually you should at least maybe think once about binary search. Let's see how binary search works in this particular problem. So what we do is, suppose we take a number, say k. What my question is it possible to go from left to right in such a way that each pile in the end each pile in the end has greater than or equal to k piles, greater than equal to k stones. The question is, if you go from left to right from 3 to n and do this kind of distribution, is it possible to ensure that after doing this allocation, each pile would have greater than equal to k stones? So this is the problem. uh, if we can do that using binary search, we can like binary search on this value k, and we can get what is the maximum stones that can be ensured in each of the piles. So that would be the answer. I hope that part is clear. So yeah, so you want to find the this way you can find the maximum stones each pile would have. And if you can find, is it possible to do the allocation such that each pile has k stones? So again, like binary search would work here, because if you can ensure that a pile has like all the piles have at least 5 stones, then using that exact same method you can ensure 4 as well. So if some way, if using some way, you can give at least 5 stones to each of the pile. Using the exact same way, each pile also have at least 4 stones, at least 3 stones, and all that. So it would be kind of 1, 1, 1, 0, 0, 0, and you have to find the maximum this can be done, so which is this particular value. So I will just show you the code, and like we will discuss how you would do that. Okay. You can see first is the simple part of binary search. So you take in the input and L equals to 0. Basically, your answer can always be 0, and it can never be this value, which is greater than all the like the maximum value your pile can be of maximum size. And then you simply do the binary search. You check for the mid. If it is possible to do that, you assign L as mid, and if it's not possible to do that, you assign R as mid, and in the end L would be your answer. Now we just have to figure out how can we ensure this thing. So since it's given to go from left to right, we must like what I did, like maybe let's go from left to right and see if we can do the allocation maybe greedily. So suppose for this particular problem, k is what? Let's take 2. Oh, okay, let's take 3. So these two I can't change. For 10, I know that it's greater than 3. So what I might do is I have to ensure that this stays greater than 3. That means I can take the remaining 7. And once I take this remaining 7, I can put 7 divided by 3 would give me D. So basically, the number of stones you take is like say X would be equal to 3D. So D would be equals to X by 3. So if you take 7 stones, you can give 2 here and 4 here. You have to give D and 2D. You can't give more or less. So this is like the maximum you can ensure them to be. And similarly, if you take 3, then you will get an excess of 97 from here, using which you can give more to them. This way, you can ensure that all of them have greater than 3. So for 3, this gives true. Let's see what we can do for, say, 5. Suppose our answer was 5. Suppose you want to check for 5. Then what we might do is, okay, let's see what's the answer for this particular. Yeah, it is 7, right? Cool. So what we might do is, we take 5 for 10, starting from 10. We see it has 5 extra stones, which I now try to divide. I would give 1 to this and 2 to this. After doing this, I can still see that my first pile does not have greater than 5 piles. That means I would never be able to do, and thus I would return false, that 5 is not possible. But you can see the answer is 7. Like even 7 is possible. And how you do that is, uh, instead of giving just 5 to this, what you can do is give give it completely. So giving 3 to this and 6 to this would make this 7, this 5, and this 0. And after that you can give like say 10 to this and 20 to this, which ensures that everyone is greater than 7. So this way you can get 7, but you could have not done it. Like if you went from left to right and do the allocation greedily, you won't get. You might think that you can maybe give all the pile completely, but that might also not work, because in this case it was 100. What if it was like no stone here or something? You might not always be able to recover from what you did. So to clear this out, what we do is we instead move from right to left. And for the last particular pile, like why do you actually do the maybe I'll just clear it up. Yeah. So we have 1, 2, 10, and 100. Now what we do is we go from right to left. And why we do that? For 100, like for the last pile, we know that it should be like say greater than equal to 5. So the number of stones in it should be greater than equal to 5. That means the 95 stones in it can always be utilized, and I can't utilize more than that because there's no one who would uh, pay this particular pile back. So I can, and greedily I must use the maximum stones. So I would use all its 95 stones and give to this and this. So this would give like what, 30 and all. So what you do is you start from right and keep on giving them. But again, the problem mentioned that you must move from left to right. This is what the problem said. So what we do is we see how many stones we could have given if we go from right to left. Say, suppose for this particular problem, 95. So you could have given 31 to this and 62 to this. Now, when you check for this one, it has 41. Say you just want to make it about 10 or like above. Okay, like suppose we want to make it about 10. Yeah, suppose we want to make it about 10. Then this has 100, which means we can take 90 from it and relocate it as 30 and 60. Now, when you come to this, it has 40 stones. You just want 10. So you would keep 10 and like maybe give 30 back as 10 and 20. And now you can see you have ensured that all the piles have greater than 10 stones. But as you can see, the answer is just 7, which means 10 cannot be done. And why that's the case? This is when, because we we went from right to left. When we're going from right to left, we are overestimating what we could have given when we come from left to right. So suppose for this case, we give 10 to like this position and 20 to this position, but that thing itself cannot be given when we are going from left to right. This pile can give a maximum of 10 stones, and it gets the additional stone from this particular pile, which it would get only after doing its operation. So that's why what we do is we find from right to left how much this particular pile can give at a maximum, and we would also compare it with what was its original value. So let me just show you the code. So bool check, it would check if it's possible to ensure that all the piles have greater than x stones. uh, uh, we just stored in the input because we would change it. So this is like a of I is the number of stones after like reallocating from uh, the piles ahead it. Now you go from right to left, from end to start, and what you do is, if the number of stones in that pile is already less than x, then you can't do anything because you have tried to do the maximum from the back. So the answer would never be possible, and you return false. If it is greater than x, then you find the difference. So ai minus x is the difference, like this is the additional stones it has, and you divide it by 3 because like you want to find the d value. So this would be the maximum stones you can give to the previous and the two previous element using the number of stones it now has. But originally it had only hi number of stones. So hi is like the original stone thing. So hi by 3 would be the maximum number of stones it can give from going left to right. Because like when you're going from left to right, a particular pile does not get any stones. It just has what it has. So this is like the stone it could have given at max. And third, you would take the minimum of them. This would give the stones you could have given from this pile to the previous piles while going from left to right. At the same time, ensuring that this pile would not miss out stones in future, and this thing would also get covered with greater than x stones. So there were these two things which you had to uh, see into and take the minimum of them. So if I is greater than 2, then like if I is 3 to n, then you would give the additional stones to the previous two piles. So to I minus 1, you give d, and to I minus 2, you give 2d. So yeah, that's the solution for this problem. I guess the binary search obviously is a bit easy to when you think of it. Even after that, the check function is a bit non-trivial. So you would have to spend some time, but you would be able to get okay why this check function work. You could have some other implementation for the check function, but I'm not sure if some other way apart from binary search is possible. So yeah, that is the solution for the problem C. Let's go on to the last problem for today, which is problem D, robot cleaner revisit, which is an interesting problem. As you can see, it has the exact same story and setup as for problem A. So we have the exact same setup. Now, what we are just given is this is the setup. What we are given is at each particular step, the robot, yeah, the robot may uh, in cleans the floor, but in each second, the cleaning operation is performed with probability p by 100 only. So at each position, it may or may not clean. It will clean the dirty cell with a position with a probability of p by 100, and not clean with a probability of 1 minus p by 100. You have to find the expected time for the robot to clean the dirty cell. So let's build up on a few things. Okay, so Suppose we are given that the robot will first encounter the dirty cell after t1 amount of time. So you start from 0. You are given that the robot will first encounter the dirty cell at t1 time from the start, then at t2 time from the start, then at t3 time from the start, t4, t5, so on up till infinity. You know all the times on which the robot will be in the same row or column as the dirty cell. That means it can clean the dirty cell. So these are all the times. Now you want to find the expected time. So this is like a standard thing in expectation. You know the probability of each event. So the robot would like get the work done in t1 time with a probability of p. P is the probability, which is p by 100 for this problem. It will get it done in t2 time in 1 minus p by 100, which is when it did not solved in, like it did not cleaned in, okay, 1 minus p for when it did not solved in t1 time into p, that it solved in t2 time. If it even didn't solve in t2 time, then it might have done in t3 time, which would be 1 minus p squared to not solve in both of the times previously into p to solve in this particular term. Similarly, you can write down the infinite series and you can get the value you want. But so again, like in this particular setup, let's see the B1, see the original diagram. So as you can see, the robot will first encounter the dirty cell here. It may again encounter in future and then again. So it will encounter a lot of time, but we don't know exactly for now in which particular timestamps. Suppose we know this infinite series, then we can use t1 into p plus, so the probability into the value, and if you take the summation over it for the infinite series, you will get the expected value. Because that's like if you get this with this probability, this with this probability, then on an expectation you are getting this. So the answer would be P into T1, this into T2, this into T3, and so on. So using this infinite summation, you can get the solution. We can even calculate the values T1, but not up till infinity. So that's one of our limitation. So we will see how that can be tricked a bit. But before that, let's see one simple thing. Okay. So suppose this is like a simple problem in expectation. So suppose you're given a toss, you're given a coin toss. You have the coin which has yeah, head on one side and tail on the other side. You will toss the coin and you will keep on tossing it until you get a head. So your task is to find the expected number of toss you would do before getting a head. Here you can see uh, with a probability of half, you will get the head in the first turn itself. With a probability of 1 by 4, like not getting in this turn and getting in this turn, you will get so basically this is like, maybe I'll just clarify it. This is 1 minus 1 by 2 for not getting in the previous turn, and 1 by 2 for getting in this turn. So this is like, yeah, the probability you will get in this turn, which, and for this time, like if you get in this turn, you have done 2 toss. Similarly for 3, it would be 1 by 8, and for 4, it would be 1 by 16, and you can do the infinite series. And if you will do the mathematics and do the summation, like 1 into 1 by 2 plus 2 into 1 by 4 plus 3 into 1 by 8, 4 into 1 by 6, which forms an AGP, you will get the sum turns out to be 2. So this is the expected number of task to do before you get ahead, but it's a bit complicated maybe in the sense that you would have to do some mathematical calculation. Let's see what smart thing we can do for this particular problem. So suppose you did the toss and you get head. So okay, um, suppose this was you. You did the toss with a half probability. You got head, and you like your value is, or your the money, or like the number of toss you did is 1. With 1 by 2 probability, you got a tail. You got a tail, and now you know that you would have to do the same thing again. So, what expectation is? The expected number of moves you would have to do before getting ahead if you start from now. So, this is again like a new stage for a coin toss. Your toss are independent from your previous toss. So now it would again take you e more steps, because so this is like we are finding this expectation value. This would be 1 with the probability of half, and with the probability of half, like with the other half, it would be 1 plus e, cos 1, because you have already done one toss, and now it would take you e further more toss to get the head. So using this, you can simply form the equation E equals to 1 plus okay, E equals to 1 by 2 into 1. With a half probability, you will get the head in one toss, and with the probability of half, you would get it in 1 plus E number of toss. And now if you just do the max, you can find is equals to 2. So this would, like, you can take 2 over there. 2e would be 2 plus e, and e would be equal to 2. So using this way as well, you got E equals to 2. Here we did not do any complicated mathematics. We just utilized the fact that E is the expected number of toss to get ahead if we start from now. Like if you just start from now, you would take E toss on an expectation to get ahead. And you just utilize that fact to get the value of E is 2. So let's see how we can utilize that particular fact here. Suppose you know the values t1, t2. Suppose you're starting from time 0, and you know you know that you will first encounter the cell at time t1, at time t3. You are at the position RB, RC. You know that at time t1, t2, t3, t4, so on, you will encounter the dirty cell. You what also you know is, after a particular time, say at t equals to mx, at t equals to mx, you would again be on this cell, which is rbrc. Okay, you can name it differently. It would be rbcb. Yeah. So you start from RB comma CB. You know that you would encounter the particular dirty cell in these timestamps at all of these times, and at t equals to mx, you would again be on the same position, this position RB comma CB. So suppose you think that expected time to find the like to clean the dirty cell is E, then E is equals to, let's suppose these are the only 4 timestamps, then E is equals to P into T1. Okay, let me write it in the notepad. Yeah, so E would be equal to okay, maybe I will just write it here itself. Yeah, E would be equal to Oops, okay, I can't do that. Yeah, E would be P into T1 for this particular time. If you get to here, the probability that you would get it done in this amount of time is 1 minus P to not get in the previous turn and P to get in this turn into T2. That would so the expectation would be P into T1 plus 1 minus P into T2 plus 1 minus P square for these to not get in these two and P to get in this turn into T3. That would be from this one plus for this particular timestamp it would be 1 minus P cube to not get in all the previous terms uh, into P to get in this term into T4. That would be for all the steps. Now you know that even after doing all this, if you are not able to get, you again reach the same state RB comma CB at time equal to mx. So what you know this, what you get is, if you were not able to get in all these turns, you are again on the same position, which would take you an expected E amount of more time. And E amount of more time, so which will make your total time as E plus mx. So with the what would the probability for this? 1 minus P raised to 4. So then expected 1 minus P into 4 probability, like with the probability of 1 minus P raised to 4, you will get the cell cleaned in E plus mx times. Now this is a simple equation. You just put like pick E over there and you would get, if you just cancel this, E would be equals to this plus 1 minus P raised to 4 into mx. All of this divided by 1 minus P raised to 4. So this is like simple linear mathematics, linear algebra, and this way you will get this equation. So what you do, so you can find out this value mx, which is basically like you would get to the same row after every 2n minus 2 step, like because like you can do that thing up. So if you are at x, if you are at this position, it would take you n minus x step to go to the last cell. You would complete back, like you would go back till 1. So this would be n minus x plus n minus 1 to go till 1 and then x minus 1 to come back to x. So this would be like x would get cancelled off and this would turn out to be 2n minus 2. So after every 2n minus 2 step, you are on the same row, and after every 2m minus 2 step, you are on the same column. So you can take the GCD, but yeah, what also means is after 2n minus 2 into 2m minus 2, after these many, like after this amount of time, you would be on the same cell again. So you will find all the time in between this T1 to whatever, which is like less than 2n minus 2 into 2m minus 2. For them, you would do this calculation and like mx would be equal to this thing. So I will just show the code that should maybe give a bit more better idea. Yeah. So this is like just a power thing to find the mod inverse. This set stores all the time which you would encounter the dirty cell on. This put time is a function, like again, x and y axis both are independent. So what you do is you take the initial and the final cell and the boundary, like the range up to which you can go before you get reflected back. There are these three variables which are basically the first time you encounter. So the first time, okay, The first time you encounter would be, say, x1 minus x2, and after that you would form a period. So you would come back at 2n minus 2x, you would again go there and come back after 2x minus 2 steps. So uh, yeah, so the first time you would come back is after 2n minus 2x step, and you would come back again after 2x minus 2 steps. So, and this would like then continue. Uh, it again come back here, goes to the end, comes back, goes to the first, comes back, and so on. So this would be in a cycle. So if x1, like if x2 is greater than x1, the first time you would encounter would be this, and your cycle would be this. Else, the first time you would encounter would be this. You go to the end and you come back. So this would be the first time, the first amount of time, after which this would be the period. And now what you do is you run an infinite loop, and like basically if it's odd you add the period 1, and if it's even you add the period 2, and you would do this until the time you are taking is less than mx. And since it has a period of n, it would occur at max 2m number of times between 2n and 2m. So this has a period of 2m or 2n into when all of this would repeat. Thus, uh, the maximum number of timestamps you would get is 2m between the complete range. Thus, you would not get a time limit basically. You would have 2m for the rows and 2n for the column. So the total number of timestamps, this total number of timestamps would be of the order n plus m, which would not be an issue because n into m itself is less than 10 is to 5. Yeah. So yeah, that way you can find all the times, and after finding out the time, you just do what we saw previously. This is the maximum value, 2n minus 2 into 2n minus 2. You find all the times, you divide p by 100, you define not p as 1 minus p, and then np is basically 1 minus p raised to I. Total is yeah, total is this particular summation. So for all the times in your set, what you do is the current expectation you will get is x, which is this value, times probability for this event to occur, times np for the previous events to not occur. That would give you the probability, the expectation from this particular time. You would add that in your total, this thing, and you would raise np to another power. So it is 1 initially, then 1 minus p, 1 minus p square, 1 minus p cube, 1 minus p raised to 4. So np basically stores that, and you keep on adding them to your total. In the end, you also add to your total np into mx, which is for this thing, and you divide it by mod inverse of 1 minus np. So this is np, this is 1 minus np, and you divide it by 1 minus np, which is mod inverse of, which is multiplying by mod inverse of 1 minus np, and that is your answer. So basically, this getting this thing is important. Getting the values of t and doing the calculation can be done. So maybe the critical thing in this question was to realize that if you reach on the same cell again, you would have the exact same expectation. Once you get that, you can do the implementation, which would take some time, but you can do it. So that's the solution for D. If you have any comments, please feel free to write them in the chat. Um, we'll try to answer it if we can. And make sure you like and subscribe to the channel. Thank you.